Hello friends, welcome to this video session of Vapour compression system. In that we will cover Vapour to liquid heat exchanger, work requirement of compressor and heat recovery methods of unit number 2. My name is Mr. S. V. Kumbar, Assistant Professor, Sharad, Institute of Technology, College of Engineering, Yadra, Ichalkaranchi. So starting with Vapour liquid exchanger. So heat exchanger is a device in which exchange of heat takes place between two fluids which are at different temperature. So in vapor liquid heat exchanger, one fluid is a gas which is normally air and other is a low pressure liquid, more commonly water, and are readily separable after the energy exchange. So in either cooling of liquid or humidification of gas, liquid partially evaporates and vapor is carried away with the gas. In this vapor liquid heat exchanger, more than 90% of energy transfer is by virtue of mass transfer because of evaporation of liquid, and convective heat transfer is a major mechanism. A wet cooling tower with forced or natural draft airflow is the most common application, and other applications are in air conditioning, spray chamber, spray dryer, spray tower, and spray pond, etc. So this is vapor liquid heat exchanger where cold liquid flows through this and cold liquid out through this. Here vapor flows in the same direction and condensate flows to this direction. These are the insert. The next part is the compressor, which is used in reciprocating that is in refrigeration system. In refrigeration system, generally reciprocating compressor is preferred. Nowadays, motor is enclosed in a single unit with compressor, and that we call it as hermetically sealed compressor. So reciprocating compressor is a positive displacement compressor that uses piston driven by a crankshaft to deliver gas at high pressure. The size of reciprocating compressor may be up to 25 HP, and it is used for light duty application. Reciprocating compressor has low mass flow rate and high pressure ratio. That's why it is widely preferred. An application of reciprocating compressor includes oil refineries, gas pipelines, chemical plants, natural gas processing plants, and refrigeration plants. So generally, an air compressor takes refrigerant at atmospheric. Now, initially, in refrigeration system, low pressure vapors of refrigerant from evaporator passes to compressor where it compresses at high pressure and high temperature, then delivers it to condenser. After condensing, then it flows through expansion valve, and after expansion valve it flows to evaporator. Now generally this working of reciprocating compressor is divided into two parts: compression without clearance volume, compression with clearance volume. So these are the basic components of reciprocating compressor. Here pressure, receiver pressure, atmospheric pressure, piston, cylinder, cooling system, water jacket, that is cooling system, and stroke volume. So displacement of reciprocating compressor is specified by its stroke volume, and actual working is shown with the help of this figure. Next point, compression without clearance volume. If we neglect clearance volume, consider a single stage reciprocating air compressor without clearance volume, delivering air from one side of the piston only. Now the compression process, we have to assume it as either isothermal, adiabatic, or polytropic, as we don't know by which process the compression of refrigerant takes place. So let's say P1 is equal to initial pressure of refrigerant, V1 is equal to initial volume of refrigerant, T1 is equal to initial temperature of refrigerant, P2, V2, T2. These are the corresponding value of refrigerant. R is the pressure ratio, that is P2 upon P1, that is final pressure upon initial pressure. Hence, the net work during the adiabatic process, polytropic process or isothermal process is given by this way, right? So this is analysis of cycle. Total indicated work per cycle is equal to P2V2 minus P1V1 upon N minus 1 plus P2V2 minus P1V1. And after solving this, we will get for polytropic process, the work required for compressor W is equal to N upon N minus 1 M into R T2 minus T1. Here, other forms of equation of indicated work is given as W is equal to N upon N minus 1 M R T1 P2 upon P1 raised to N minus 1 upon N minus 1. That is simplified form as N upon N minus 1 P1V1 into bracket P2 upon P1 raised to N minus 1 upon N minus 1. So indicated power. The indicated power is the work done on the air per unit time. Therefore, indicated power is equal to N upon N minus 1 MR T2 minus T1. Mechanical efficiency is the ratio of indicated power to shaft power, and shaft power is equal to indicated power plus friction power. Remember, shaft power is the power supplied to electrical motor to compressor during refrigeration, and motor efficiency is the ratio of shaft power to input power, that is electricity, and input power is in the form of electrical power supplied to electrical motor. So this is all about work required which is supplied to reciprocating compressor. If the compression takes place by isothermal process, then generally isothermal efficiency is taken into consideration. So it is the ratio of isothermal power to indicated power, and isothermal work done is given by these formulae. W is equal to P1V1 ln V2 upon V1, that is P2V2 ln V2 upon V1, that is P2V2 ln P1 upon P2. These are the different forms of work done during isothermal compression. Now coming back to waste heat recovery opportunity. This is the last point of second unit. So first of all, we have to identify sources of waste heat, that is combustion exhaust, process exhaust, hot gases from the drying oven, cooling tower water. These are the different sources of waste heat. After that, after finding source of waste heat, second important thing is we have to identify recovery technique, that is whether we have to go for regenerator, recuperator, economizer, waste heat boiler, thermoelectric generator. After recovery technology, in use of recovered heat, the heat which is recovered, how to use that heat, that we have to identify by using preheating, that is boiler feed water, raw material, combustion of air, electricity supply, domestic hot water, etc. So by this way we can go for heat recovery opportunity. So these are the different waste heat sources: combustion exhaust, process of gases, cooling water from furnaces, air compressor and internal combustion engine, conductive, convective and radiative losses from equipment, conductive, convective, radiative losses from heat products like hot cokes, blast furnaces. And use of waste heat energy can be used for combustion of air preheating, boiler feed water, preheating, load preheating, power generation, steam generation for use, space heating, water preheating, transfer to liquid or gaseous process stream. Factors affecting waste heat recovery feasibility. So first one, the quantity of heat that has to be used, that first factor, it is affecting heat temperature and quality. So heat temperature is the final temperature and the quality of heat which has to be extracted from any system. Next one is the composition. One more factor is minimum allowed temperature. Remember, heat flows from high temperature to low temperature. So the minimum temperature from which we have to extract heat, that is a factor. Operating schedule, availability and other logistics. Means if boiler is working continuously, then we can extract heat continuously. Similarly, if refrigerator is working continuously for 24 by 7 hours, then and then we can go for heat recovery from its condenser, and we can use that heat for other purposes. So this is high temperature heat recovery, types of devices and temperature range. Nickel refining furnaces, the temperature recovery we can go for 1370 to 1650. This is high temperature recovery. For aluminum refining surface, zinc refining surface, copper refining surface, steel heating surface, open hearth furnace, cement kiln furnace. So these are the high temperature heat recovery which is generally obtained from furnaces. So waste heat recovery can be also done with Rankine cycle. So in Rankine cycle, generally evaporator is provided here. So in the with the help of condenser, heat is used. This high pressure, high temperature vapors of refrigerant, it flows through evaporator. After that, heat is exchanged, heat is recovered here, and this high pressure, high temperature vapors expands in the blades of steam turbine or turbine where it generates electricity. Low pressure vapors are condensed in the condenser. Again it is pumped back. Again it evaporator. Waste heat from process. It can be used for generation of vapor, and again it is sent back to that is turbine. Medium temperature heat recovery. Generally, medium temperature heat recovery is obtained from steam boiler exhaust, gas turbine exhaust, reciprocating engine exhaust that is turbocharged, heat treatment furnaces, drying or baking ovens, catalytic crackers, annealing furnaces. And the temperature region is given here starting from 230 to 650, that is medium temperature heat recovery. And in low temperature heat recovery, generally in case of refrigeration and air conditioning, low temperature heat recovery can be achieved, that is here 32 to 43 degrees centigrade. And these are the different sources from which low temperature heat recovery can be possible with temperature zone it is given. Now waste heat recovery technologies. So first one, a recuperator. So recover exhaust waste heat in medium to high temperature applications such as soaking or annealing, melting furnaces, afterburners, gas incinerators, radiant tube burner and reheat furnaces. So recuperators can be based on radiation, convection or combinations of radiation and convection. So generally, recuperators are constructed out of either metallic or ceramic material. Metallic recuperators are used in application with temperature below 2000 degree Fahrenheit, that is 1093 degree centigrade, while heat recovery at a temperature is better suited to ceramic tube recuperator, and this can operate at high side temperature as high as 1538 degree centigrade and cold side at up to 982 degree centigrade. So here metallic radiation recuperative design is shown here. Flue gas flows through this middle region. At the same time, cold air flows like this and hot air flows to from this region. So this is actual radiation recuperator installed at glass melter. This is one more, that is convection recuperator. Here combined radiation and convection recuperator is used. and hot air is used for process. Regenerators. In a regenerator, one example is shown here. Fuel flows like this here to the burner, and burner sends heat to the air, and once air is heated, it is used for final application. So regenerators are most frequently used with glass furnace and coke ovens, and were historically used with steel open hearth furnace before these furnaces were replaced for more efficient design. They are also used to prevent the hot blast provided to blast stove used in iron making. But however, regenerators in blast stoves are not a heat recovery application, but simply the means by which heat released from the gas combustion is transferred to the hot blast air. Regenerator systems are specially suited for high temperature application with dirty exhaust. One of the major disadvantages of this regenerator is that it requires large size and high capital cost, which are significantly greater than cost of recuperator. So heat wheels, that is rotary generators. These heat wheels or rotary generators operate similar to fixed regenerators in that heat transfer is facilitated by storing heat in a porous media and by alternating the flow of hot and cold gases through the regenerator. Use of heat wheels. It uses a rotating porous disc placed across two parallel ducts, one containing hot gas, other containing cold gas. The disc composed of a high heat capacity material which rotates between the two ducts and transfers heat from the hot duct to cold duct. Hot wheels are generally restricted to a low and medium temperature application due to thermal stresses created at high temperature. This is all about heat wheels. Next one is passive air heater. In passive air heater, gas to gas heat recovery devices for low to medium temperature applications are used, where cross contamination between gas stream must be prevented. The application of this passive air preheater is in oven, steam, gas turbine, secondary recovery from furnaces, etc. So there are two types of passive preheaters, the plate type and heat pipe type. First we will see plate type heat exchanger. In plate type heat exchanger, hot waste gas and cold air in flows alternatively to plates. It consists of multiple parallel plates that create separate channel for hot and cold gas stream. Hot and cold flows alternately between the plates and allow significant area for heat transfer. They are often bulkier and more costly and more susceptible for following problems. Second, heat pipe heat exchanger. In heat pipe heat exchanger, refrigeration cycle is used once again for heat recovery purpose. So figure is shown here. In heat pipe, heat recovery can take place with the help of evaporation and condensation. Here, in this case, condensation takes place of this vapor and heat is liberated, which can be used for different purposes. And in evaporation, heat is absorbed, refrigerant is converted into vapor, that vapor is condensed. Here, heat is used for final application. The heat pipes are heat exchanger consist of several pipes with sealed ends. Each pipe contains capillary wick structure that facilitates movement of the working fluid between the hot and cold ends of the pipe that we have already studied. The hot gas passes over one end of the heat pipe, causing the working fluid inside the pipe to evaporate. Pressure gradient along the pipe cause the hot water to move to other end where the vapor condenses and transfer heat to cold gases. The condensate then cycles back to the hot side of the pipe via capillary action. This is the actual capillary tube which is generally used in most of the mechanical applications for waste heat recovery purpose. Second, economizer with finned tube heat exchanger. Generally, economizer is used to preheat the water, and that preheated water can be used for different application. Now, economizer used to recover heat from low to medium temperature exhaust gases for heating liquid. Applications of economizer include boiler feed water, preheating, hot process liquids, hot water for space heating or domestic water heater. Economizer consists of round tube with attached fins that maximize maximum surface area and heat transfer rate. Liquid flows through the tube and receive heat energy from hot gases flowing across the tube, and in this way the liquid gets heated. That heated liquid can be used for different applications. Waste heat boiler. This waste heat boiler is shown in the figure, which uses medium to high temperature exhaust to generate steam. Waste heat boilers are available in variety of capacities, allowing for gas intakes from 1000 to 1 million feet cube per meter. In case where the waste heat is not sufficient for producing desired level of steam, auxiliary burners or afterburners can be added to attain higher steam. The steam which is used in waste heat boiler can be used for power generation. Low temperature energy recovery option and technologies. So there are various applications where low grade waste heat can be cost effectively recovered for the use of industrial facility, generally in refrigeration and air conditioning. The large quantity of waste heat available in the range of 38 to 200 degrees centigrade. Much industrial waste heat is in the low temperature range. For example, combustion system such as boilers, or in case of refrigeration and air conditioning system. Large quantities of water which can be found in industrial cooling, water and cooling air. Example is cooling of air compressor with account of for about 18 British tons unit. One of the integrated steel mill in Japan successfully installed a power generation plant with 3.5 megawatt capacity using cooling tower at only at 98 degrees centigrade. In the case of combustion of exhaust gas, substantial heat can be recovered if water vapor contained in the gas is cooled to lower temperature. Minimum temperature limit around 120 to 150 degrees centigrade are frequently employed in order to prevent water in the exhaust from condensing and depositing corrosive substances on the heat exchanger surface. So this is heat pump that we had already studied in first unit. Heat pump is a device which extracts heat from a low temperature reservoir and it supply that heat to high temperature reservoir so that the temperature of hot surface is kept above atmospheric temperature. This is all about heat pump. In the evaporator, the heat is extracted from the heat source to boil the circulating substance. The circulating substance is compressed by the compressor, raising its pressure and temperature. The heat is delivered to the condenser and the pressure of the circulating substance is reduced back to the evaporator condition in the throttling valve where the cycle repeats. Thermocompressor. Thermocompressor compresses low pressure steam by very high pressure steam and reuse as a medium pressure steam. So the example of thermocompressor is shown here. This is suction steam which is sucked here and it uses converging diverging part where its pressure is converted to velocity. So nozzle for acceleration of high pressure steam to a high velocity fluid is used and discharge steam can be used for different applications. And last point is challenging to recovering low temperature heat. So first challenge is related to corrosion of heat exchanger surface. While extracting heat from low temperature sources, as water vapor contained in the exhaust gas cools, some of its some of it will condense and deposit corrosive solid and liquid on the liquid exchange surface. The heat exchanger must be designed to withstand exposure to these corrosive deposits. This is generally require advanced material. This is first challenge. Second challenge is large heat exchange surface required for heat transfer. Generally, while recovering low temperature waste heat, we require large surface area. So in many applications, it is not possible to have such large surface area. And third one, finding a use of low temperature heat. Recovering heat in the low temperature range will only make sense if plant has a use for low temperature heat. Potential end uses include domestic water heater, space heating, low temperature process heating, etc. So these are the challenges while extracting heat from low temperature waste heat. So this is all about today's video lecture. Thank you. Thank you very much.